Hi everyone. Today I want to share a little background information about a property in Haskell, yes, I guess a property called let should not be generalized. And this is provoked by a conversation this week on a GHC ticket, which will be linked in the description. So first, we'll describe the ticket and then sort of go into this let should not be generalized and what that's all about. So there's sort of a curious feature, I guess, in GHC today. Inconsistency. We'll call it an inconsistency. If I make a GADT here, so here's a GADT that if I pattern match on MookG1, let's call it actually MookGint, then it's going to tell me that my argument to G, my parameter to G is int. If other MookG other, we don't learn anything. Okay, so here's that definition. But of course, there's a bunch of errors. Let's add gadgets. Oh, good, we're green. That was easy. Now I want to go to another module, and I'm going to import GADT, and then write a little function that operates on this. So we're going to have f take in. Let's see. We need both of these on the screen at the same time, I think. Come on. Okay, so we're going to have some function f that takes a GA and returns, it can take an A and a GA, and it's going to return an int. So fx blah equals x. Well, that's not going to type check, right? Because I don't know that x is an int. Couldn't match expected type int with actual type A. But if I pattern match on mookgint, that tells me that A really is int, and so this will work. Except that there's a funny thing here. A pattern match on a GADT requires the gadgets or type family's language extension. Well, first off, it's a little weird that it's saying gadgets or type families. I mean, should sort of choose one. Type families aren't around at all. And the other strange thing about this is that generally GHC has a principle, a design principle, that we require an extension to write a construct, but not an extension to use one. So it's not all that unusual that I need to enable GADTs to use this, but sort of looking at this, other than some type inference stuff, all the features that we see here are a plain old Haskell 98. And yet GHC requires an extension. So that's really the crux of what this is about. So I'm going to turn on gadgets here. And then now we're going to get a pattern match incompleteness problem. And so we need to do the other one. Here we're going to have mookg other. And now I don't know anything about that first parameter, so I just have to return some constant. Okay, so this is a way I can define a correct function f based on G. Let's go back over here, and now I'm going to make a pattern synonym to abstract over mookgint. But this is not really a talk about pattern synonyms, but that's where the ticket comes from. Okay, so I'm going to say pattern patsyn. We'll just call it patsyn. And let's see, given what we learned last time, or in the pattern synonym videos, perhaps you haven't watched those, that's okay. So this is going to take a universal A and no required constraints, and it's going to produce A is an int and GA. That looks like the right type. Let's just move this. Okay, and pattern patsyn equals mookgint. Okay, and now I'm sure it's complaining because we don't have pattern synonyms enabled. Oh, and here it'll probably want rank n types or something like that. Okay. Okay, good. So it's happy with this. This is happy. So now I should be able to change mookgint into patsyn. And I can, but now I'm going to get pattern match incompleteness again. So we have to have a little complete pragma over here. Complete patsyn and mookg other. That covers G. So now that I've done that, my warning goes away. Everything is good. Okay, no real surprises yet. The surprise is that I can get rid of that and it still works. So this is a bit unusual that here now, why did I need GADTs if I'm using the actual GADT constructor? But if I just sort of hide it behind a pattern synonym, now I don't. That's the ticket. The ticket says, this is inconsistent. Let's fix. And originally the fix suggested was that we should follow this principle within GHC, that we require the GADT's extension to define, but not to use. So in other words, the suggested fix to this inconsistency was to make it so that if I type this, this would now compile, instead of complain that we need to turn on an extension. However, not all is well. And to understand what is not well, we're going to have to go into a bit of a diversion, and this is where we're going to find let should not be generalized. So let's comment this out. We will return. And we can combine these all now, I think. Oops, I don't want that. I still don't want that. I want this. Okay. Let's see. So let should not be generalized. First, let's look at, if I write a function like this, GHC infers a more general type. So one type for f is int arrow int. But of course, it's not going to infer that. It's going to infer the most general type, p arrow p. Okay, that's not really a surprise. Let's say we have something slightly more complicated. Let's say fx equals let gy equal xy in g3 g false. So let's not get overloaded numbers into the mix. Okay, we'll do this. So let's see, what are we going to get here? So we have f infers this general type. A goes to a tuple, a pair of a car and a bool. Right? That's not all that much of a surprise, because can we figure out, oh, the type of G is B, is a function from B to a pair of AB. What's slightly strange about this type of G is that B is locally quantified here, but A is not. And I don't know of a way offhand to configure HLS to show me that fact. I bet if I put something in ghci.conf somewhere, I could make it happen, but I'm not going to do that right now. So instead, we just sort of look here that if x has type A, and this x still has type A, this B is locally quantified within G. Oh, and by the way, isn't it nice that I can see what the type of G is just by pointing at it? It's sort of hard to extract this in GHCI, for example. Okay. And we know that G has to be quantified over B. B has to be worst for all B, because I've applied G at type car and at type bool and all as well. Now, a strange thing is going to happen if I enable gadgets. Just by enabling gadgets up here, now suddenly couldn't match expected type car with actual type bool. Just to sort of show that this is really what's going on, if I comment out the language extension, now everything is green. With the language extension, now this program is no good. And I haven't misspelled the language extension or something crazy like that. What's going on here is that the GADTs extension enables another extension called MonoLocalBinds. So I'm going to get rid of GADTs, and I'm just going to try on MonoLocalBinds, which is an extension that most people would never write, but it is implied by GADTs implies MonoLocalBinds, and type families implies MonoLocalBinds. So maybe that recalls something from a few minutes ago when it said add gadgets or type families. So what's going on here is that when MonoLocalBinds is in effect, if we have a local definition such as G that mentions a bound variable from an outer context such as X, that G will not be generalized. So this false here, it's saying, oh, that's no good. But if I actually just remove the X, now everything is okay, because I haven't triggered this condition. So I'll just sort of write that out. MonoLocalBinds means when a local definition mentions a variable from an outer scope, the definition will not be generalized. And so here I've gotten rid of the X, and so now it does not mention a variable from an outer scope, and so it can be generalized, and all is well. I can specialize G. If I point at G, I can get its type. It's just P arrow P for any P, and I can apply it at car and at false. On the other hand, if I have this X here, now G is car to a car. And that's because it first sees that G is applied to a character, and so it uses that to infer the non-generalized type of G. So then, of course, the question is, why on earth do we have this? And to do that, we're going to have to explore yet another example. So now let's have H here. So we're going to say Hx equals let Jy equal x equals x, comma y in Oh, what do I want to do here? We're going to need h, x, g. I have to sort of figure out exactly what I'm doing here. So it's going to take some variable of type A. Then it's going to take GA that we imported, that GA. And, oh, it's going to return something or other. We're not sure. I'm not sure yet what it will return. And here, now we're going to do in case G of mcg int J true, we'll say, mcg other, and false true. Okay, let's see. Does this type check? Aha. Here is the question. Does this type check? So let's walk through it. So we have X is going to have type A. G is going to have type GA. So that means that when I pattern match on G, just like we have an F up here, when I pattern match on G, we're going to learn something about A. Now I define a local function J, which operates, which takes a Y, and it just sort of returns that Y over here, but it checks to see if X equals itself. So of course, for this to make sense, we need eq A to hold. Right? We can only do this if eq A holds. And this J is going to return bool and then whatever it was passed. So the question is, since the only call of J is here in mcg, and let's actually enable GADTs because that's not where the problem lies. This is accepted. I was not expecting this to be accepted. Oh no, it's not accepted. There's a bug. There's an error here. To use this, use partial type signatures. Well, let's just put the bool or the bool comma bool. I still think it's going to not work. Yeah. Where was I? Over here, when I call J, I know at this point that X is really an int. An int does have an eq instance, so it does make sense for me to compare X against X over here, and yet we can't do that. And that's because GHC is going to try to infer the type of J. This is a small bug in HLS. It really shouldn't be talking about any. It's going to try to infer the type of J without knowing that A is really an int. But it turns out I can, with enough special magic here, if I say that, and if I turn on scope type variables, now down here I can give J a type signature that will make sense. J says, as long as eq A holds for this A that's bound up here, then this takes a bool and returns bool, bool. With this type signature, actually this program is accepted. We've gone green. If I remove this type signature, then we are in trouble. And we don't know we don't know how to do this. And the problem is that GHC would normally try to generalize this type. This here is well, I guess this isn't the most general type. The most general type would have B here and B there. I can actually say for all B. And just to show you, this type still does work. I hope, yes, it does. But to be able to do this, we need to have generalized this type, and then we need to infer quite a strange type here. It's strange because it mentions a class constraint on a variable that's not bound here. It's on a variable that's bound up there. We could perhaps teach GHC to do this, but it turns out that if we do this all the time, we're going to get some very strange behavior, and actually users don't really expect it. So I'm going to have a link in the description to some more information about why inferring this type is no good. But this is exactly the case covered by MonoLocalBinds. And MonoLocalBinds says, no, GHC, do not try to generalize this type. We're going to get strange effects if we try, so don't even try. The reason that this is important is because we want type inference to be predictable. So if we were to generalize this type and get something other than this sort of more complicated type that would be hard to get, well, then would it expect A to always be an int? Maybe we get a type that looks like, we might also get a type that looks like this. Does that work? That also does work. right? We could just say that A really must be int here. So that's yet another type. Which one is better than the other? It can be a little bit hard to say because it also depends on what information we're going to get about A when we pattern match on it later. No, 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 no. So we have MonoLocalBinds, which says don't even bother. GHC requires us to enable the GADT's extension in order to pattern match on the GADT. It really doesn't care about the GADT's extension. What it cares about is MonoLocalBinds. So maybe it should be changed to only require MonoLocalBinds, not GADTs. But it's this MonoLocalBinds that makes type inference predictable in the presence of GADT pattern matches. So going back to that ticket where we started, what should we do for these pattern synonyms? Well, these pattern synonyms introduce these local equalities just like GADT constructors. So I've advocated on the ticket that we should actually require MonoLocalBinds in some form in order to get a pattern match on a pattern synonym with a provided constraint that is an equality. Or actually, I guess any provided constraint really should require this according to the logic sort of all laid out here. So this is a little bit of a dark corner, but this is really what's going on. This is why when you enable GDT, sometimes other strange things happen. Once in my Haskell career, I actually specifically disabled MonoLocalBinds by saying no MonoLocalBinds, and that was because I did really want generalization in cases like this. It was a bit of an odd case. I'm not going to explore that today. Anyway, I hope this has been interesting. Thanks very much for watching. Bye.